Hello everyone. In this section, I'd like to explain the formation process of protostars. We consider the spherical regions. Some of the materials at the centers start collapsing. Material at the center collapse to form a region with high densities. We consider this is a protostars. The information is transferred to the outer regions, but the speed to transfer the information is limited. The information propagates with the sound speed of A. In the regions exterior to the wavefront, express the R equal AT. The materials remains in an isothermal equilibrium state. As an initial condition of the molecular cloud, we assumed isothermal. This means temperature is constant inside of this region. When we study structure and evolution of stars, round T, round R is expressed minus 3 over 480 kappa rho over T cube times F over 4 pi R squares. In this equation, kappa is correspond to the opacity. Opacity is really small. It means round T, round R becomes small. Derivative of T with respect to R is small values. So this means temperature is constant. So we assume the temperature is constant in the molecular cloud. So we'd like to consider the isothermal equilibrium structure of self-gravitating spheres. So we use the two equations. First one is the Euler equation. Is the equilibrium state. 0 equal minus round P round R. This is the pressure gradient terms. Is balanced with the gravitational force minus gm rho over R squares. Then m is a mass inside of a sphere with a radius of R. We combined these two equations to find structures of self-gravitating spheres. So 0 equal minus round P round R minus gm rho over R squares. So from this equation, use a chain rule. Round rho, round rho, round R equal minus rho gm. M is a mass inside of the R, so m as a function of R over R squares. The round P round rho is equal to the sound speed a squares. So from this equation, you can divide it rho and multiply the r squares in the both sides of the equations. So r squares 1 over rho round r equal minus g over a squares m as a function of r. Then you can find the derivative in the both sides of the equations. d dr r squares 1 over rho round r equal minus g a square dm over dr. Then actually we consider some spheres with a radius of r. Then inside of this mass is r. Then if you consider that with a dr, the volume of this spherical rings is expressed 4 pi r square. Surface area of a sphere with a radius of r times dr. This is the volume. So the mass inside of these rings can be expressed density times volume. You can express this is equal to the rho times 4 pi r squares. Then this part is expressed d log rho over dr. Then equations becomes d dr r squares d log rho over dr equal minus 4 pi g over a squares. A is constant. Now we consider the isothermal equilibrium. Temperature is constant. R square rho. Now we assume the form of the densities. Rho as an expression of the A R to the minus B power law functions. So you can take a log in the both sides of the equations. Log A minus B log R. So from this equation, if you take a derivative of the log rho with respect to R, it becomes minus B over R. Then you can consider this equation of once. Left hand side of equation 1, it becomes d dr. So find the derivative. So this is minus b r. So it becomes minus b. And the right hand side of equation 1 becomes minus 4 pi g over a squares a times r to the 2 minus b. So both sides have to be equal. So minus b equal minus 4 pi g over a square times a. There is no r dependence in the left hand side. So 2 minus b have to be equal to the 0. So from this B is equal to 2, and the capital A becomes 2 pi g over A squares. From this equation, density rho as a function of R is expressed. Capital A is A square over 2 pi g, and B is 2, 1 over R squares. This is the density distributions of isothermal equilibrium of self-gravitating spheres. For the M is integrate 4 pi R prime square rho R prime dr. Then you perform this integral calculations. It's 2A squares over g times R. Okay, so this is the mass inside of a sphere with the radius of the R. And the density profile is given by the A square over 2 pi g times 1 over R squares. So we have discovered density profile, the outer regions of spheres. We discovered density profile of isothermal equilibrium of a molecular cloud. So this is the initial conditions before forming protostars. At the central regions, density increasing because of the material start falling toward the centers. So density profile in the inner region is given by the falling object. We calculate the falling speed using the conservation. Kinetic energy is given by the potential energy. So 1 over 2 v square equals gm over r. So falling speed is given by the square root 2gm over r. So falling speed is proportional to the r to the minus 1 over 2. So inner regions has a higher speed compared with the outer regions. So for the outer region to fall toward the centers, it takes longer times. So during the falling process of outer regions, the mass inside is a constant. So if you consider the spherical ring is falling, then inside of the capital M is always constant. So we call that this is the inside-out collapse. Capital M of the mass is a constant values. Then we consider steady mass accretion rate. M dot is a constant values. This means that there is no accumulation at any special positions. At the centers, mass is accumulating. So mass accretion rate can be calculated. Minus 4 pi r square rho v. So this is going to be the constant values. So from these equations, you can easily calculate the density profile of the inner regions. 4 pi r squared rho v. So v is a proportion to the r to the minus 1 over 2. Proportion to the r squares rho r to the minus 1 over 2. So this is rho to the r 3 over 2. So this have to be the constant values. To be constant, have to follow the proportional to the r to the minus 3 over 2. Then mass accretion rate becomes a constant values. We summarize what we discover, the density profile. At the inner regions, density profile follows power laws. Outer regions, that are initial condition for the density of isothermal equilibrium self-gravitating spheres. So if you compare power index, minus 2 is smaller than the minus 3 over 2. So if you extend this region, this is the initial profile we expected. The mass in this region, actually this falls toward a star, and the star is forming at the centers. Actually, we could integrate from the outer region and then make a numerical simulation to find out the transitions from this density profile to the another density profile. Then by making such numerical calculations, Frank should find out the relation between the mass migrating toward the stars and the mass remained in a molecular cloud. Mass ratios 0.975, the remaining part is 1.025. So if you sum up these two mass, it becomes 2. So this 2 comes from these 2. So among these two, 0.975 go to a stars, and 1.025 is still remained in a molecular cloud. This was calculated by the Xu 1977. It is published in the UpJS. Actually, mass accretion rate is given by this equation. Mass accretion rate is 0.975 A cube over G. Then if you consider temperature of the molecular cloud is 20 Kelvin. then you can calculate the accretion rate of a stars is going to be 2 times 10 to minus 6 solar masses per years. So it takes about 5 times 10 to 5th, 500,000 a year to build up a solar mass stars. I explained density profile of an isothermal equilibrium of a self-gravitating spheres. Once the central region becomes denser, gravity becomes stronger at the central regions and the materials start falling to the centers. Density of a central region is approximated by the power law of the R to the minus 3 over 2. And the outer region keeps the same power law of the isothermal equilibrium. Law is proportional to the R to the minus 2. Okay, this is the first section of the formation of protostars.